After World War II, with most of Europe in ruins, tension grew between the Soviet Union and the United States. It was clear that the next global superpower required the ability to both launch and successfully defend nuclear attacks from intercontinental ballistic missiles. In North America, the most vulnerable point of attack was over the North Pole. So in 1958, a joint effort between United States and Canada was established, known as NORAD, or North American Aerospace Defense Command. An important line of defense was the semi-automatic ground environment. It was an automated system of over 100 long-distance radars scattered across North America. They were connected to computerized radar stations that transmitted tracking data using telephone lines or radio waves. All of this radar information was fed into a primary warning center buried a mile deep inside Cheyenne Mountain in Colorado. This application of machine-to-machine communication allowed operators to make split-second decisions using information transmitted and processed automatically by computers. This idea of being online was quickly adapted and advanced by universities in the following years as they understood the potential of computer networking.
The thing that makes the computer communication network special is that it puts the workers, the team members who are geographically distributed, in touch not only with one another, but with the information base with which they work all the time. And this is obviously going to make a tremendous difference in how we plan, organize, and execute almost everything of any intellectual consequence. If we get into a mode in which everything is handled electronically and your only identification is some little plastic thing you stick into the machinery, then I can imagine that they want to get that settled up with your bank account just right now and put it through all the checks, and that would require a network.
Money transfers were just one of a growing number of applications which required encryption to remain secure. And as the internet grew to encompass millions around the world, a new problem emerged. At the time, encryption required two parties to first share a secret random number known as a key. So how could two people who have never met agree on a secret shared key without letting Eve, who is always listening, also obtain a copy? In 1976, Whitfield Diffie and Martin Hellman devised an amazing trick to do this. First, let's explore how this trick is done using colors. How could Alice and Bob agree on a secret color without Eve finding it out? The trick is based on two facts. 1. It's easy to mix two colors together to make a third color. And 2. Given a mixed color, it's hard to reverse it in order to find the exact original colors. This is the basis for a lock. Easy in one direction, hard in the reverse direction. This is known as a one-way function. Now, the solution works as follows. First, they agree publicly on a starting color, say yellow. Next, Alice and Bob both randomly select private colors and mix them into the public yellow in order to disguise their private colors. Now, Alice keeps her private color and sends her mixture to Bob, and Bob keeps his private color and sends his mixture to Alice. Now the heart of the trick. Alice and Bob add their private colors to the other person's mixture and arrived at a shared secret color. Notice how Eve is unable to determine this exact color since she needs one of their private colors to do so. And that is the trick. Now, to do this with numbers, we need a numerical procedure, which is easy in one direction and hard in the other. This brings us to modular arithmetic, also known as clock arithmetic. For example, to find 46 mod 12, we could take a rope of length 46 units and wrap it around a clock of 12 units, which is called the modulus, and where the rope ends is the solution. So we say 46 mod 12 is congruent to 10. Easy. Now, to make this work, we use a prime modulus, such as 17, Then we find a primitive root of 17, in this case 3, which has this important property that when raised to different exponents, the solution distributes uniformly around the clock. 3 is known as the generator. If we raise 3 to any exponent x, then the solution is equally likely to be any integer between 0 and 17. Now, the reverse procedure is hard. Say, given 12, find the exponent 3 needs to be raised to. This is called the discrete logarithm problem. And now we have our one-way function, easy to perform, but hard to reverse. Given 12, we would have to resort to trial and error to find matching exponents. How hard is this? Well, with small numbers it's easy, but if we use a prime modulus which is hundreds of digits long, it becomes impractical to solve. Even if you had access to all computational power on Earth, it could take thousands of years to run through all possibilities. So the strength of a one-way function is based on the time needed to reverse it. Now, this is our solution. First, Alice and Bob agree publicly on a prime modulus and a generator, in this case 17 and 3. Then, Alice selects a private random number, say 15, and calculates 3 to the power 15 mod 17, and sends this result publicly to Bob. Then Bob selects his private random number, say 13, and calculates 3 to the power 13 mod 17 and sends this result publicly to Alice. And now the heart of the trick. Alice takes Bob's public result and raises it to the power of her private number to obtain the shared secret, which in this case is 10. Bob takes Alice's public result and raises it to the power of his private number, resulting in the same shared secret. Notice they did the same calculation, though it may not look like it at first. Consider Alice. The 12 she received from Bob was calculated as 3 to the power 13 mod 17. So her calculation was the same as 3 to the power 13 to the power 15 mod 17. Now consider Bob. The 6 he received from Alice was calculated as 3 to the power 15 mod 17. So his calculation was the same as 3 to the power 15 to the power 13. Notice they did the same calculation with the exponents in a different order. When you flip the exponent, the result doesn't change. So they both calculated 3 raised to the power of their private numbers. Without one of these private numbers, 15 or 13, Eve will not be able to find the solution. And this is how it's done. While Eve is stuck grinding away at the discrete logarithm problem, and with large enough numbers, we can say it's practically impossible for her to break the encryption in a reasonable amount of time. This solves the key exchange problem. It can be used in conjunction with a pseudo-random generator to encrypt messages between people who have never met.